The topic is probability. I have a question for you, as usual. Did you get 50%? Did you get that in like 30 seconds? See how you get that in 30 seconds. The point is that you have to take two cases. One, when A is telling the truth and B is lying, and two, when A is lying and B is telling the truth. The catch is that if any one value is 50%, A and A bar each will be 0.5. And B plus B bar would always add up to 1, no matter whether it is 40%, 30%, or whatever. Therefore, the value is always going to be 0.5 times 1. The answer is always going to be 50%. Just for conceptual clarity, let's solve it. 0.5 times 1 minus 0.4 plus 1 minus 0.5 times 0.4. See, this is 0.5. This is also 0.5. And 0.5 times we get 0.6 once and 0.4 once. Eventually, the answer will always be 50% when any one of these two values is 50%. Let's now start from the basics. Probability quantifies the likelihood that an event will occur. Probability of an event E occurring is NE divided by NS, where NE is the number of favorable events and NS is the number of total events, the sample space. For example, what is the probability of getting an ace when a card is drawn from a pack of well-shuffled 52 cards? Number of favorable events, NE, is 4. Number of total events, the sample space, is 52. So the required probability is 4 50-seconds, or 1/13. Let's start with some logical questions around probability. Look at this question. What is the probability that a leap year will have exactly 52 Sundays, 53 Sundays, and 54 Sundays? Please pause the video and solve these three questions. A leap year has 366 days, so there will be 52 complete weeks. There will be 52 weeks and 2 days. See, these 2 extra days will be 2 consecutive days, so they cannot be both Sundays. Therefore, probability of 54 Sundays is going to be 0. So what are the possibilities for these 2 days? They can be Sunday, Monday, can be Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday, Thursday, Friday, Friday, Saturday, and Saturday, Sunday. So which of these 7 are favorable cases? Saturday, Sunday is one favorable case. Sunday, Monday is another favorable case. Out of total 7 possible cases, there are 2 favorable cases. So for exactly 53 Sundays, the probability is 2/7. And for exactly 52 Sundays, the other 5 cases apply. So the probability for exactly 52 Sundays is 5/7. These are the 3 answers: 5/7, 2/7, and 0. We hope you got all 3 correct. Look at the next one now. Probability that A shoots a target is 1/3. Probability that B shoots the same target is 1/2. What is the probability that? 5 different questions here. Please pause the video and solve all 5. A hits, B doesn't. So we need A times B bar. A is 1/3. B bar would be 1 minus 1/2, which is 1/2. The answer is 1/2 times 1/3 equals 1/6. Both hit means A times B, so that's 1/3 times 1/2. That's also 1/6. This 1/2 is different from this 1/2. This is B, and this is B bar. That is 1 minus 1/2. Although the value turns out to be the same, 1/2 in each case, mathematically they are different. Next question. None hits. So we need A bar times B bar. A bar would be 1 minus 1/3, that is 2/3. B bar would be 1 minus 1/2, that is 1/2. So the answer is 1/2 times 2/3 equals 1/3. Next, the target is hit. 2 ways of solving this one. One way is to take 3 cases. A hits, B doesn't, plus A doesn't, B does, plus both hit. So either add the 3 probabilities, or a simpler way would be 1 minus neither hits. So this would be 1 minus A bar times B bar. A bar is 2/3. B bar is 1/2. This turns out to be 1 minus 1/3, which is 2/3. See, probability for the target is hit can be seen as 1 minus none hits. We found none hits was 1/3. Therefore, the answer is 1 minus 1/3 equals 2/3. Exactly 1 hits means A times B bar plus A bar times B. Again, the same thing. If one value is 1/2, the answer here is always going to be 1/2 because the value of B bar and B is 1/2 each, and A plus A bar would be 1. So eventually, it will be 1/2 times 1 equals 1/2. The value will always be 1/2 in such cases. Another question. A smart way of solving this question would be to figure out the probability of the bullseye not being hit. In one throw, the probability of being hit and not being hit. The probability of being hit is 1/2. The probability of not being hit is also 1/2. In two throws now, rather than finding this, it's better to find this. The probability of not being hit even once would be 1/2 times 1/2 equals 1/4. Therefore, probability of being hit would be 1 minus 1/4 equals 3/4. This is a smarter way. Otherwise, we will have to take three cases: that it is hit in the first throw but not the second throw, or it is hit in the second throw but not the first throw, plus that it is hit both the times. So, that would take a lot of time, and the number of cases will dramatically increase in higher number of throws. A better way is to figure out the probability of not being hit, and then 1 minus probability of not hit will get us the probability of being hit at least once. In 3 attempts, this would be 1/2 times 1/2 times 1/2. This would be 1/8, and this would be 7/8. So you can see that the probability is increasing. In one throw, it was 50%. In 2 throws, it became 75%, and in 3 throws, it is 87.5%. In 4 throws, this would become 1/16, and therefore this value will become 15/16, which is greater than 90%. So the answer is that she must throw the dart 4 times, or she must throw 4 darts. Look at this one now. Please pause the video, solve it yourself. Simple set theory question. Very often, probability is asked through set theory examples. If you are good with set theory, probability is just an extension. Largely, such questions are set theory questions. In all, there are 100 people we know. Tea only is 30. Coffee only is 20. Mocha only is 15. 5 drink none of the 3. And 10 drink all 3. What is the probability that a person picked up randomly drinks exactly 2? So these 3 are the remaining parts, and these 3 represent exactly 2. So see 30, 50, 60, 75, 80. So there are 20 out of 100 people who drink exactly 2 of the 3 drinks represented by these dots. So the required probability is 20% or 0.2. A very interesting DS question here. Please pause the video and solve it yourself. Here are the 2 statements. There are 4 types of children, boys and girls. Boys with black eyes, I'm calling them BL, and boys with brown eyes, I'm calling them BR. Similarly, girls with brown eyes and girls with black eyes. I am using the second alphabet for brown, so I'm using R, second alphabet of brown. Black, I'm using L, the second alphabet of black, because black and brown each have B as the first alphabet. So that's just my nomenclature to make the terms easier to understand and avoid confusion. Now, I know that, of course, the sum of 4 probabilities is 1. This is known to me. The question is asking whether a girls with black eyes. This probability is greater than probability of boys with brown eyes. That is what the question is. Look at statement number 1. It simply means that BL plus GL is greater than BR plus GR. Of course, too many variables. Nothing much can be said about whether GL is greater than BR. Both the possibilities exist, yes as well as no. So statement 1 is not sufficient. Look at statement 2. It says black-eyed boys. So BL is less than GR. Again, this is too little information to answer the question to say anything about what the question is asking. So alone, statement 2 is also not sufficient. Let's combine the 2 statements and check. So on combining, we know that the sum here is greater than the sum here. We also know that BL alone is less than GR alone, but the sum is greater. Therefore, GL must be greater than BR. So on combining, we could get to an answer. That yes, GL is greater than BR. Girls with black eyes are greater in number than boys with brown eyes. Combining worked. Therefore, C is the correct answer choice. Next, the concept of areal probability. It is applied when you need to find the probability of a specific area out of a total area given. The required probability is desired area divided by total area. Let's understand this through a live problem. You may want to pause the video and solve it yourself. You have the coordinate axis here, a rectangle. 0, 0 is here. And 8, 6 means, let us say this is 2, 4, 6, 8. This is 2, 4, 6. So this is the required rectangle. This is the complete area. We need to find the part of this area where the y-coordinate is greater than the x-coordinate. How do we do that? Let's draw an x equals y line. Yes, this would intersect at 6, 6. Now imagine, below this line, this area has x-coordinate greater than y-coordinate. Therefore, this is the desired area. This is where y-coordinates have values greater than the respective x-coordinates. So the area of this triangle out of the area of the complete rectangle is the desired probability. The denominator is the area of a rectangle with dimensions 8 by 6. And the numerator is the area of a right triangle with base times height 6 by 6. Solve it. You get 3/8. That's the answer, 3/8. Very interesting questions can be made on this concept of areal probability. Remember, the required probability is desired area divided by total area. Conditional probability represents the probability of an event B when it is known that another event A has already occurred. In such cases, the sample space is not the total number of arrangements or cases. Rather, it is only those cases which satisfy the first event. Let's understand it through an example. Look at this question. 3 cards are drawn from a pack of 52 cards. What is the probability that, in the first case, all honor cards, if it is known that all cards drawn are red cards? So in normal case, we would have taken 52C3 as the denominator. Out of 52 cards, 3 have been drawn. But then, you see, a condition has been given, that it is known that all cards drawn are red cards. So not all 52C3 cases must be considered. Only those cases which satisfy the given condition must be considered. If it is known that all cards drawn are red cards, there are 26 red cards. Therefore, the denominator should be only 26C3. Now, out of these 26 cards, there are 8 honor cards, 4 diamonds, and 4 hearts. Therefore, the number of favorable cases would be about in how many ways out of these 8 red honor cards? 3 can be selected. So the answer is 8C3 divided by 26C3. That is the correct answer. One more question. If it is known the no card drawn is a picture card, there are 3 picture cards in each suit. So in all the 4 suits put together, there are 12 picture cards. So as per the condition given, these 12 cards have to be discarded. Therefore, the denominator is no longer 52C3. It is only 40C3. The 12 picture cards have been discarded, and out of these 40 cards, the only honor cards which are left are aces. So the favorable cases are no longer 16C3. They are only 4C3. The 4 aces, only they should be considered. This is the required answer. Now let's look at some permutations and combinations based probability questions. Look at this one. There are 4 parts to this question. Please pause the video and solve it yourself. This requires knowledge of permutations and combinations. I hope that you have seen the P&C video earlier. The denominator in all the questions will be the total number of cases, which is 10 factorial. So the first question, denominator is going to be 10 factorial. In all the cases. 5 boys are together, and 5 girls are together. So in all, there are only 2 groups. The 2 groups can be shuffled in 2 factorial ways. Now, each group can be shuffled in 5 factorial ways. So this is the required answer. Look at the second one. No two boys are together. So as I explained in the P&C video, in such cases, first arrange elements on which there is no restriction. So girls do not have any restriction on them here. So in this case, first have the girls seated. 5 girls can be seated in 5 factorial ways. Now for boys, there are 6 places, always an extra place because of the 2 corner positions. Out of these 6 places, boys can take any 5 places. So 5 factorial times 6p5 divided by 10 factorial is the required answer. Next, 2 particular boys are always together. So you have in all 9 elements, 8 boys, 8 elements, and 2 boys together, forming 1 element. So these 9 elements can be arranged in 9 factorial ways, and the 2 boys who are together can be arranged between themselves in 2 factorial ways. The denominator is, of course, 10 factorial. Next, 2 particular girls are never together. So we need 1 minus probability of the cases when they are together. Probability of 2 elements being together is same as that in the last question. This is the probability of these 2 girls being together. So 1 minus this would give us the probability of they not being together. Look at this question. There are multiple parts. Please pause the video and solve all the 4 questions. Out of 8 balls, 3 are being chosen. Therefore, the denominator in all the questions is going to be 8C3. All are red. That means that out of 5 red balls, 3 are being chosen. This is the first answer. Next, 2 red, 1 white balls. So out of 5 red balls, 2 are chosen simultaneously. So multiplication sign. Out of 3 white balls, 1 white ball is chosen. Denominator continues to be 8C3. Next, all are of same color. So 2 different cases, 5C3 and 3C3. This is for the case when all 3 are red. This is for the case when all 3 are white. This entire sum divided by 8C3. See, we have taken the addition sign here because there are 2 different independent cases. Remember, whenever you have the AND scenario, multiplication sign comes in. Whenever you have OR scenario, the addition sign comes in. So see here we have the case that all 3 balls are red or all 3 balls are white. Or, therefore the addition sign. Next, at least 1 is white. So we can find 1 minus the probability of no white. Therefore 1 minus the probability of all red. So 1 minus 5C3 divided by 8C3. Else you can also find the probability of 1 white ball, 2 white balls, 3 white, and then add all the 3 cases. That would lead to the same value, but take a bit longer. This is a smarter way of solving it. Look at the next one. It's a very interesting question. The card-based questions are not asked on GMAT because in some parts of the world, the game may not be very popular. But I still take this example in my sessions because there is a lot to be learned from this. If you can solve all the 8 variations here, you really understand probability as well as permutations and combinations. Now, denominator in all or most of the cases would be 52C3. 3 cards are being drawn out of 52. Denominator is that. All aces. There are 4 aces in a pack of 52 cards. Out of 4, 3 are being drawn. So 4C3 divided by 52C3. That's the required probability. Next, all are of the same denomination. In all, there are 13 denominations. So 13 times the probability for each denomination. The probability is 4C3 divided by 52C3 for each denomination. Because for each denomination, there are 4 cards, out of which 3 can be chosen in 4C3 ways. Next, all are of same suit. There are 4 suits, and each suit has 13 cards. Out of 13, 3 cards can be chosen in 13C3 ways. The denominator is, of course, 52C3. Next, same color. There are 2 colors, and for each color, there are 26 cards. So out of 26 cards, 3 can be chosen in 26C3 ways. Denominator is again 52C3. Next, 2 red and 1 black card. So out of 26 red, 2 red cards have to be chosen. Out of 26 black, 1 black card has to be chosen. See, the question says and 1 black. Therefore, the multiplication sign divided by 52C3, that's the answer. Look at this one. A very interesting question. No king or queen. That means out of 44 other cards, 3 can be chosen. But from these cases, we have to subtract the cases in which there is no ace. So 40C3 would be the number of cases with no queen, no king, no ace. 44C3 is the number of cases with no queen or king. Therefore, the difference will give you the number of cases with no queen, no king, but at least one ace. A very, very interesting question, this one. Denominator would be 52C3. The next two questions are from Conditional Probability. In Conditional Probability, the entire sample space doesn't apply because some condition is given. The condition given here is that it is known that all cards are red cards. Therefore, the denominator will not be 52C3, it will be 26C3. Look at the numerator now. Jack, Queen, King, Ace. In all, there are 16 honor cards, but we can consider only the red honor cards. So in the numerator, we will have 8C3. A very interesting question based on conditional probability. In such cases, the sample space reduces as per the condition given. The sample space does not include all 52 cards. It includes only red cards. Therefore, the denominator as well as numerator includes conditions as per the given scenario. In this case, it's given that only red cards are drawn. So in denominator, 26 red cards. In numerator, we have 8 red honor cards, out of which 3 are being selected. 8C3 divided by 26C3. That's the answer. Look at the last one. Try solving it yourself. It's given that no card drawn is a club, and therefore the denominator will no longer be 52C3. It will be only 39C3 because it has been given that clubs have to be discarded. In numerator also, we will not take cases where clubs are involved. So in all, there are 16 honor cards, but removing the club's honor cards, there are only 12 honor cards. So the required probability is 12C3 divided by 39C3. Look at the next one. Please pause the video and solve it yourself. Two ways of solving this. One is to solve it mathematically. Imagine a 6-digit number. The first place can be obtained by 9 digits from 1 to 9. The second place can be obtained by any of the 10 digits, 10 digits, 10 digits, 10 digits. And in case of multiples of 5, for units place, only 2 digits, 5 or 0, or otherwise all 10 digits. So the required probability is 9 times 10 to the power of 4 times 2 divided by 9 times 10 to the power of 5. That's 1/5. However, I would suggest that think of it intuitively. Every fifth number is going to be a multiple of 5. Therefore, the answer is going to be simply 1/5 only. Look at the next one. Intuitively, this question can be solved very easily. Mathematically, it will take forever. The point is that P and H cannot come one upon the other. They have to be in an order. In half the cases, P will come first and H will come later, somewhere later in the word. And in half the cases, H will come first and P will come later. So quite intuitively, the answer is simply 1/2. Look at this question. This question is a bit different from the last one because it says P comes immediately before H. So P and H have to come together in this order. In all, there are 7 alphabets. So denominator is going to be 7 factorial. Numerator would include 5 other alphabets, and these two coming together as 1, so 6 elements. These 6 elements can be shuffled in 6 factorial ways. Remember, don't multiply this by 2 factorial. We would have multiplied if the question said P and H come together. In that case, they could have swapped their positions. In this case, P has to come before H. Therefore, multiplied by 2 factorial will not apply. The answer is 1/7. Look at this question here. There are 2 parts. The first part is quite simple. Look at the denominator first. What's the total number of cases? 7 different chocolates. So every chocolate has 5 choices. First chocolate has 5 choices. Second chocolate also has 5 choices. And likewise, the 7th chocolate also has 5 choices. Total 5 to the power of 7 ways. So the denominator is going to be 5 to the power of 7. Numerator. Imagine there are only 5 ways. The first child gets all chocolates, the second child gets all chocolates, and similarly the fifth child gets all chocolates. There are only 5 cases out of 5 to the power of 7 cases that meet the given condition. The answer is 5 divided by 5 to the power of 7 equals 1/5 to the power of 6. Second part is a bit more complex. There are 2 possible cases. One case is that 3 children get 1 chocolate each, and then 2 children get 2 chocolates each. The second case is that 4 children get 1 chocolate each, and 1 child gets 3 chocolates. So first, let us figure out the number of ways in which children can be selected for such a distribution. Imagine there are 5 children, out of which 3 are to get 1 chocolate each, and 2 are to get 2 chocolates each. So either you select these 3, this can be done in 5C3 ways, or you select these 2, which can be done in 5C2 ways. Or imagine in all there are 5 entities, out of which these 3 are similar and these 2 are similar. See, whichever way you do it, the value will be 10 only. Similarly here, either you select 4 children who are going to get 1 each, so 5C4 ways, or select 1 child who is going to get 3, so 5C1 ways. Or imagine there are 5 entities, out of which 4 are similar, so divide 4 factorial. Either which way, you are going to get 5. Now cases for children have been counted. So now it's about distributing the chocolates. We had 7 chocolates, out of which 1 is given, so 7C1, 6 remain. Next, 1 more is given, so 6C1, 5 remain. Next, 1 more is given, so 5C1, 4 remain. Then 2 are given, so 4C2. The last part is always 1, 2C2 or 1. In this case, out of 7 chocolates, 1 is given, 6 remain. 1 more is given, 5 remain. 5C1, 4 remain. 4C1, 3 remain. And the last part again would be 1. So the value is 7 times 6 times 5 times 4 times 1. Sorry, this is 6 times 1. Let me do it quickly for you. 7, 42, 210, 1260, 1260. And remember, this 10 has to be multiplied, so 10 times 1260. Or means addition, and here it is 7 times 6 times 5 times 4 times 1. So 7, 42, 210, 840. Then times 5, so 840 times 5, that is 4,200. So 4,200 for the second case, and 12,600 for the first case. Total, 16,800. The answer is 16,800 upon total number of cases. 5 to the power of 7 is the total number of cases. So the answer is 16,800 divided by 5 to the power of 7. The numbers got really big. The GMAT won't throw such big numbers at you. The number of chocolates would probably not be 7, it would be something like 5. The number of children would not be 5, it would be something like 3, maybe. But of course, if you can deal with such big numbers, you can solve easier versions of this problem very, very comfortably. Let us now solve a bunch of questions based on derangement. Please pause the video and solve these yourself. You have 5 letters and 5 envelopes. All 5 letters go into wrong envelopes. So that is in fact asking D of 5, the number of derangements for 5 elements. Applying the formula, we get 5 factorial times 1 minus 1 factorial plus 1/2 factorial minus 1/3 factorial plus 1/4 factorial minus 1/5 factorial. Solve it, or as I explained in the P&C video, it's good to know the value of D of 1 through D of 5. D of 1 is 0, D of 2 is 1, D of 3 is, let me calculate quickly, it would be 2. D of 4 is 9, and D of 5 is 44. Beyond 5, I have never seen a question testing such a big value. So D of 5 turns out to be 44. That's the first answer. The second answer, 4, go into wrong envelopes. That means 1 goes into the right envelope. So out of 5 letters, 1 that goes into the right envelope should be selected first. This can be done in 5C1 ways, and the other 4 need to be deranged. We need 5C1 times D of 4. D of 4 we know is 9. So the answer is 5 times 9. The answer is 45. Next, 3 go into wrong envelopes. That means now 2 go into the correct envelopes. So 5C2 for selecting 2 letters that go into the right envelopes. And now the other 3 can be deranged in D of 3 ways. 5C2 is 10. D of 3 is 2. So the answer is 10 times 2 equals 20. Next 2 letters go into wrong envelopes. So either select 3, which go into the right envelopes, or select 2, which go into wrong envelopes. The same thing, the value is 10. I have selected 3, which go into the right envelopes, and therefore the 2 which go into the wrong envelopes, derangement for 2 elements, this is 1. 5C3 is 10. D of 2 is 1. So the answer is 10 times 1 equals 10. Next, 1 letter goes into wrong envelope. Do you think that is practically possible? That's never possible. Because if 1 letter goes into the wrong envelope, the letter for which that wrong envelope is the right envelope will also go into a wrong envelope. Therefore, either 0 or at least 2 letters need to go into wrong envelopes. Practically, this is never possible. So the probability is 0. Last case. All letters go into right envelopes. This is of course possible in only one case, when each of the 5 letters goes into the corresponding respective right envelope. That's possible in only one case. If you got all 6 correct, you really understand the concept of derangement. Kudos. And remember, this is a probability question. We have only discussed the numerator so far. For finding out the probability, all these answers have to be divided by total number of cases, which is of course 5 factorial. So all the values should be divided by 5 factorial to get the correct probability. So this is a right bunch of answers.